Section 4.3 of James Stewart's calculus textbook has to do with various derivative tests that you can do to find out whether a function is increasing or decreasing, whether it has a maximum or a minimum, and so forth. And these can be very practical when you are trying to, for example, if you're graphing a function that has to do with profit, knowing at what kind of circumstances you're going to have a maximum or minimum profit, that sort of thing can be very helpful and very practical. So we start with the increasing decreasing test in this section. Again, very commonsensical. If the derivative of a function is greater than 0 on a particular interval, then you know that the function is increasing on that interval. This makes perfect sense because the derivative of a function is the plot of its slope. And so if the slope is positive in a particular interval, then you know that the function is increasing over that interval. By the same token, if the slope of a function is negative on a particular interval, if it's less than 0, then you know that the function is decreasing over that interval. Very commonsensical, and yet doing this test helps you know if the function is increasing or increasing. And this can be a positive thing to know. So if you identify the critical numbers, what are the critical numbers? If you remember, a critical number is a place where the slope is 0 on a particular function. And of course, where if you have a graph that's going up and then it goes down, then the slope is going to hit 0 at the maximum. Or if you have a function that's going down and then it comes up, again the slope is going to go 0 where it turns, and that's going to be a minimum. Critical numbers are also the beginning and end points of an interval. So if you identify the critical numbers on a particular interval, and then you investigate how the sign of the derivative changes as you move between those critical numbers, it's going to give you a very good sense of how the function is behaving. So for example, if you look at how the sign of the derivative is from negative infinity to the first critical number, and then what is the sign of the derivative from the first to the second critical number, if there is a second, then from the second to third, and so forth, maybe from the fourth to positive infinity. If you look at how the sign changes of the derivative on various intervals between the critical numbers, this gives you a good sense of where the maximums and the minimums are, and so forth. So the first derivative test basically puts everything on the previous slide together and says that if the derivative of a function changes from positive to number at critical number c, then that is a local maximum. Again, this makes perfect sense. If the slope is going up, if the slope of the function is positive, so that the function is going up, and then the function hits a critical number, and then the function starts going down, and the slope becomes negative, you know that that's a turning point. That's where it's hit a peak, and then it started going down. Same thing that if a function changes from negative, that is that the function's going down, it has a negative slope, and then it hits a critical number, and then the function turns up and has a positive slope, then you know that it has a local minimum at c. It's gone down, hit the bottom, and then gone back up. This is called the first derivative test, and it helps you know about maxima and minima of a particular function. Now if the derivative of a function doesn't change sign at a critical number, then the function doesn't have a local maximum or minimum at that point. So there you have that. Now this leads us to some tests involving second derivatives. That is, if you take the derivative of a function. First, some definitions. If something is concave upward, that means the function line is above all of the tangents to it. It's easier just to think of it as a U type thing. It doesn't mean it has to look like a perfect U. It could be quite spread out. But basically, if the function is catching the rain and looking up, then it is concave upward. If it is emptying the rain, if it's an upside down U of it doesn't have to again look like a perfect upside down U, but if basically it's curving to where if you put something out into it, it would just fall right out, then you know that the function is concave downward. And in that case, then the line of the function is going to be below all the tangents to the line. So those are some basic definitions of what concave upward, concave downward is. Now here we go with the concavity test. If the second derivative is greater than 0 for all the x on a particular interval, then the graph is going to be concave upward. It's going to be like a U. If the second derivative is less than 0 for all x on an interval, then the graph is going to be concave downward. Why? The first one tells us that the slope is increasing, and so the curve is getting higher. The second one tells us that the slope is decreasing, which means that it's going increasingly downward. And so again, if you understand what we're talking about here, so the first derivative is the slope. The second derivative is whether the slope is getting steeper or less steep. So if the slope is getting more steep, then the second derivative is going to be positive. If the slope is getting less steep, then the slope is going to be negative. And this is what concave upward and concave downward basically mean. So the roller coaster, is where the slope is getting steeper, more positive, and the roller coaster going down is where it's negative. So that's the concavity test. And if we put everything we've done all together, we have the second derivative test, which says that if the first derivative at a critical number is 0, so that's a horizontal slope, and if the second derivative is greater than 0, then the f has a local minimum at c, because the slope is now going to start going up like a roller coaster at that number. Now, if the derivative is 0, so you've got again, a slope is horizontal, and the second derivative at that critical number is less than 0, then f has a local maximum at c, because it's going to start going down. And so that's the second derivative test. So an inflection point, this is the final thing to say about this section. An inflection point is where a continuous curve changes from one concave orientation to another. So it goes from being concave down to being concave up, or it goes from being concave up to being concave down. That's an inflection point where it flips its concavity. That is, of course, neither a local maximum or a local minimum. It's just a point where the second derivative changes from positive to negative, or the second derivative changes from negative to positive. So this is section 4.3 of James Stewart's calculus textbook.